Hey everybody. Hope you all are doing well. Do the usual things. Where'd you go? Here's the usual attendance and tutoring links, as well as the link to the end of the quarter evaluation. Once again, please fill it out if you haven't already. Let's see, I was looking at Sanders' stuff, posted a new homework. Also, I know you guys have a final quiz. When is that due? I was trying to see here. I can't quite tell. Let's see. Let me look at this. 6th. Okay. Which is what? Sunday? I think that's right. Let me double check. Saturday. Okay. Okay. Actually, let me write that. I'm gonna write that down because I'm trying to figure out exactly what my availability is gonna look like for finals. Sanders final quiz. Let's do the 6th. Okay. Yeah. Sorry. One sec. What I'm thinking is that, so, sorry, my brain. Okay. So here's my thought. Classes, so the last day of classes is Thursday. So next week we have class Monday and Wednesday. However, my plan is on Friday and then the following week to hold like office hours for availability for students. And since your guys' test or your final quiz is due on Saturday, I would definitely have office hours for you guys on Friday. So I think I will definitely plan on having office hours during our usually scheduled class times for sure, and probably more than that. But I would say everyone is certainly welcome to come to regularly scheduled class on Friday at 10 o'clock. But you certainly don't have to. I mean, you don't ever have to come, right? But your attendance isn't required on Friday. But if you want to come on Friday, ask questions that are not exactly the quiz questions, but questions that have the same sort of gist to them. We can certainly do that on Friday if you guys want. So I will plan on doing that. And yeah, so I will do that for sure. I'll probably also schedule some other office hours, and I'll make a Zoom meeting for those and send you guys a link. And those will be available to you guys and probably also to other students. I'm trying to figure out what my other students have in their finals as well. I think a lot of them feel like they're really early, so we'll try and do as much as we can. All right, homework 8. I assume you guys have questions about homework 8. I was looking at it. There's a lot of L'Hopital's rule stuff. There's a little bit of graphing stuff, inflection points, and then there's some optimization stuff. So what do you guys have questions about? Sure. Yeah. So I definitely, yes, for sure. I've got 2 problems that are similar. Like I know exactly what kind of problems that are similar, but not exactly the same. So my pens. I wish, like, I like the whiteboard. It's really great. I just wish this black dust did not get everywhere. It's just so kind of gross. I'm going to throw this little carpet I got down here in the wash because it's covered in just black dust. It's terrible. Okay. So let's look at one similar to 5 and then similar to 6. So here's one that's very similar to 5. The limit as x approaches 0 from the right of the square root of x times the natural log of x. And something you all should be aware of is that, so first and foremost, we can't use L'Hopital's rule. Oh, sorry, my screen isn't. Let me fix my screen so you guys can see what I'm writing. Sorry about that. There. Now you can see what I'm writing. Oh, let me fix my view so I can see what I'm writing the right way. Sorry, I just closed my video. I'll fix that in a second. There's my fun little picture a student drew of me many years ago. Okay, here we go. All right, so optimization, we can definitely talk about that too. So whenever you're thinking you might even want to use L'Hopital's rule, you have to be able to write the expression as a fraction, right? I could never use L'Hopital's rule here because I don't have a fraction, right? You can't take the derivative of this and the derivative of this when they're multiplied together. They have to be divided. But before that, even we have to think, do I even need to use L'Hopital's rule? So if I plug in 0, what do I get? Well, this is going to be like a 0. X squared of 0 is 0. And the natural log of 0, or the natural log of function as x gets closer and closer to 0, what happens to the natural log function as x goes closer and closer to 0? Anybody know? Do we get really big? Do we get really small? Do we get close to 0? Do we get close to 1? Here's the attendance stuff again. So this is an important one that I feel like students and people, actually not just students, people in general, have a hard time remembering. With the natural log function, as x gets close to 0, the natural log function goes to negative infinity. The way I remember it is by the graph. Oh, have I showed you guys this graph thing? I probably haven't. Maybe I have, I don't know. So if you look at your right hand, my hand is not great for this. So what to do with a hand with less lines on it might be better. But if you look here, this looks like a natural log function. And if you look here, this looks like an e to the x function. This has to be your right hand, not your left hand. So again, we've got natural log of x and e to the x. So the natural log of x function looks like this. Has an intercept at 1, 0. But specifically, as we're getting closer and closer to 0 from the right, the function is going down to minus infinity. And 0 times infinity, or minus, when I say infinity, you should mean plus or minus infinity. 0 times any sort of infinity is an indeterminate form. Because again, this isn't really 0, this is a really small number. This isn't really negative infinity, it's just a very, very large negative number. And we don't really know which one's kind of overpowering the other one, or if there's some intermediate balance. So what we have to do is we have to rewrite this as a fraction. And my rule of thumb is that you never want to bring the natural log thing down to the denominator. You always want to bring an e to the x thing down to the denominator. And then x to a power is kind of, usually comes down to the bottom unless you have an e to the x in the bottom. So I write this as natural log of x over 1 over the square root of x. Now I'm going to rewrite it so it's easier to use L'Hopital's rule on. My pens are all have many pens. So this looks good. So the limit as x goes to 0 from the right of the natural log of x over, instead of 1 over the square root of x, I'm going to write this as x to the negative 1/2. And now it should be semi-clear here that we can use L'Hopital's rule. And the reason we can use L'Hopital's rule this way is because we have a fraction, and also because it's the right type. It's either 0 over 0 or an infinity over infinity. In this case, it's infinity over infinity, because we already know the top is going to minus infinity, and the bottom, well, we've got 1 over 0, but it's a positive 0, right? The square root of a slightly positive 0 is a positive 0. Square root can't be negative. So this is going to positive infinity, this whole expression here. So I've got an infinity over infinity, which means we're allowed to use L'Hopital's rule. But you have to have that or a 0 over 0. Anything else won't do. So then we're going to use L'Hopital's rule. Again, I encourage you to write this L'H when you're actually using L'Hopital's rule. And we're just going to take the derivative of the top and the derivative of the bottom. Right? We're not using the quotient rule. We're just saying derivative of the top, derivative natural log of x is 1 over x. Derivative of x to the negative 1/2 is negative 1/2 x to the negative 3/2. Okay, here's the thing with a natural log over a power of x. Once you use L'Hopital's rule once, you usually don't have to use it again, because there's usually some simplification that can be done. In this case, I can write this as the limit as x goes to 0 from the right of 1 over x over negative 1 over 2 times x to the 3 halves. And then I can flip and multiply by the, multiply by the reciprocal of the denominator. That's right. Copy dot flip, something like that. The limit as x goes to 0 from the right of 1 over x times the reciprocal of this, which is 2x to the 3 halves over negative 1. I can cancel x, right? X to the 3 halves divided by x. I'm going to get x to the 1 half. So I have the limit as x goes to 0 from the right of 2 divided by negative 1, which is negative 2 times x to the 1 half. And then I can just plug in 0, because 0 to a positive power, not a negative power, but a positive power. 0 to a positive power is just 0. So plugging in 0, I get negative 2 times 0, which is 0. So in this case, the answer is 0. The one on the homework, which is number 5, is very, very similar. It's just going to be slightly different because it's a square root of x minus 1 and a natural log of x minus 1. But when you take the derivative of, like when you rewrite it, you're going to rewrite it as the natural log of x minus 1 over 1 over the square root of x minus 1, or really x minus 1 to the negative 1 half. When you use L'Hopital's rule, you're going to get 1 over x minus 1, and you're going to get negative 1 half x minus 1 to the negative 3 halves, and then you can cancel the appropriate amount of x minus 1. And you'll end up something you probably end up with something like negative 2 times x minus 1 to the positive 1 half. And then you'll plug in 1 and you get 0. So that's how that one should work out. Let's look at something similar to number 6. Unless, I should say, are there any questions about this before we move on to number 6? I'm going to start writing the number 6. So let me know if there's questions about this. Let's see, the limit as x approaches. What do I want to do here? We've got cotangent minus cosecant. That seems not fun. So let's do limit as x approaches pi over 2 of secant x minus tangent x. Oh, pi over 2 from the, it doesn't matter which side we approach from. Let's say pi over 2 from the left. Okay. And so just so that we can see this, what was I going to say here? So it's important to know that secant of pi over 2 and tangent of pi over 2 are both undefined, right? So remember, secant of x is 1 over cosine of x. Tangent of x is sine x over cosine of x. And if we plug in pi over 2, cosine of pi over 2 is 0. So this is going to 1 over 0. This is going to also 1 over 0. Right? Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So this is like an infinity minus infinity. And it is a positive infinity, right? If we're approaching pi over 2 from the left, we're a little bit smaller than pi over 2. So we're in the first quadrant still, which means all of the trig functions are positive. So this is what's called an infinity minus infinity indeterminate form. And again, infinity minus infinity can be anything. It can be 0, it can be infinity, it can be 5, it can be 2, it can be whatever. Once again, we have to rewrite this so we have a fraction before we can even think about using L'Hopital's rule. So, and actually this provides the clue. We're going to write secant as 1 over cosine, we're going to write tangent as sine over cosine. So I'm going to rewrite this as the limit as x approaches pi over 2 from the left of 1 over cosine x minus sine x over cosine x. Really, I should just put that together in one shot, right? And written it as the limit as x approaches pi over 2 from the left of 1 minus sine of x over cosine of x. And now we can hopefully see that it is of the form where we can use L'Hopital's rule. If I plug in pi over 2, sine of pi over 2 is 1, 1 minus 1 is 0. Cosine of pi over 2 is 0. So I have a 0 over 0 type, and I'm allowed to use L'Hopital's rule. So then I'm going to do L'Hopital's rule. It's still the limit, or you should be writing the limit every step until you're actually finding the value. The derivative of the top is, let's see, the derivative of sine is cosine. So I get negative cosine of x over sine, sorry, negative sine of x. Okay, here we have to be extra. Let's cancel the negative sign so that we can easily do that. So I get cosine over sine. And if I plug in pi over 2, I get cosine of pi over 2, which is 0, over sine of pi over 2, which is 1. So I'm getting 0. Interesting. I guess that's done. Yeah, I want to ask you another one that's similar, but not quite the same. So let me ask you guys. Yeah, that sounds terrible. I want to say, so let's do, I want to just do another one real quick. Limit as x approaches 0 from the right. Sure. What did I want? I wanted, sorry, it went away. Sorry, I know I had the thing that I wanted. I just want to make it simple. I want sure. I want this one. I want the limit is x. I probably want one more step, but whatever. The limit is x approaches 0 from the right of sine of x over cosine of x minus 1. Now, I want to point this out because it's important that we're careful here. So I plug in 0, sine of 0 is 0, cosine of 0 is 1, 1 minus 1 is 0. So it's a 0 over 0 type, so we can't use what we call. Limit is x goes to 0 from the right. Derivative sine is cosine of x. Derivative cosine of x is negative sine of x. And this is a place where people often try to use L'Hopital again, but we can't. If I plug in 0, I get cosine of 0, which is 1. And if I plug in 0, I get sine of 0, which is 0. So I'm getting a 1 over 0. Now, that's an undefined, it's not indeterminate anymore. When you get something over 0, I should say, when you get a non-zero number over 0, we know the answer is going to be some sort of infinity. So the question is it going to positive infinity or negative infinity? Well, let's ask. So if we're approaching 0 from the right, it means we're a little bit bigger than 0, which means we're still in quadrant 1. And in quadrant 1, every trig function is positive. So obviously cosine is positive, right? But more importantly, sine is positive, so negative sine is negative. So this is actually a small negative number, which means that this is going to negative infinity. And you might be more convinced if you saw the graph, which I think is worth looking at. So let's pull up Desmos real quick here. Share my screen. That's not something I wanted. So if we graph the original function, which was sine x divided by cosine x minus 1, you can see that as we approach 0 from the right, the function goes down, 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 down to negative infinity. On the other hand, if the limit had been the limit as x approaches 0 from the left, it would have ended up being positive infinity. So to approach 0 from the left, cosine is still positive, but then if you're approaching from the left, you're in the 4th quadrant instead of the 1st quadrant. Sine is negative, so negative sine is positive, you get a positive or positive, which is positive infinity. So just something to be aware of is that sometimes you don't get a 0 over 0 anymore, and you have to just say, oh, I've got a number over 0 that's going to go to some sort of infinity. It doesn't happen a lot, but it does happen every once in a while. So there's two problems, very similar problems with 5 and 6. Let me go back to the. I see someone asked about an optimization. So let's do some optimization. Optimization, I won't lie, gets to be is a little bit, it's a process for sure. Like there's usually, it's not just like a simple wham bam, you're done. You have to really kind of, there's a lot of pieces. To me, it feels a very similar in like the type of process as related rates, because you kind of have to draw a picture, you have to label things, you have to, for related rates, you're trying to find a relationship between the variables. For optimization, you're trying to find a function you're trying to optimize, and then a function that's a constraint. So let's look at this example. A rectangular box with a square base and no top is to be constructed with 108 square inches of material. So when someone says 108 square inches of material, you should be thinking, oh, they're talking about the surface area. Right? The surface area of the box is 108 square inches. Also, square inches should also scream, oh yeah, that's a surface area or an area, because inches squared is always a measurement of area. So inches cubed is always a measurement of volume. What dimensions of the box will maximize the volume? Okay, so first things first, I'm going to draw a picture. The base is square. So I'm thinking, all right, I've got some square base. Sorry, I didn't really draw the base first. So there's my box, and the base is square. So when I start labeling, I don't know the dimensions of the box. So when I start labeling the edges, I should remember, oh, if the base is supposed to be square, that means this side here, if I call it X, this side should also be X because it's a square base. But the height is not the same, right? So the height, I'm going to use a different variable for, called Y. I want to use as few variables as possible, but still give things that we know are different or could be different names. Okay. So I always like to start off by writing the equation of the thing I want to maximize. So I'm trying to maximize volume. And the equation for volume, at least in this particular picture, is just length times depth times height, right? It's for any kind of rectangular box or cube, it's always just the 3 dimensions multiplied together. That's going to be x times y, or x squared times y. And here's something important to remember. The thing you're trying to maximize should never be set equal to a number. We don't know what it is. We're trying to find the biggest number it can be. There's another thing that gets set equal to a number that's called the constraint. The constraint is some limiting piece of information. In this case, it's how much surface area we have, but sometimes it's how much volume we have, or sometimes it's we want this thing to be as close to this other thing as it can be, right? So there's always some kind of piece of information that says, oh, we are limited or constrained in some way, shape, or form. So our constraint here is the surface area of the box is 108 square inches. So we're going to find an equation for the surface area, and then we're going to set that equal to 180 square inches. So the surface area for a box like this is just all the areas added up together. So it's the bottom area, which is x squared, plus the front area, which is x times y, plus the side area, which is x times y, plus the back area, which is x times y, plus the left area, which is x times y. So there's 4 of those x times y's. And if there was a top, I would add on another x squared and have 2x squared plus 4xy. But since we said the box doesn't have a top, there's only these 5 sides. And so we say that x squared plus 4xy is equal to 108. And then what we do is we use the constraint if we can. And usually we can. Sometimes it's weird, but usually we use the constraint to isolate one variable. And in this case, what's going to be easier? Is it going to be easier to isolate y, or is it going to be easier to isolate x? Or I should say, is it easier to solve for y or is it easier to solve for x? Definitely. Definitely easier to solve for y. So this word's like a weird glare. I'm trying to figure out where it's coming from. Sorry, I'm like moving around here. Oh, it's from like the windows, I think. Yeah, it's weird. Sorry, and I'm like messing with things. When you stand closer, things change. I move far away, things change. Okay. Yeah, solve for y. So I'm going to isolate this term. So I'm going to have 4xy equal to 108 minus x squared and divide by 4x to get y equal to 108 minus x squared, all divided by 4x. And I might simplify this, but I might wait until I plug it into the volume equation. So how do you know what equation to use? Are we just expected to know? I'm assuming your question is about the equation for the volume or for the surface area. I guess either way, you kind of at least, so here's what I'll say generally, is that for shapes like this, for cylinders, for boxes, for cones, for spheres, there is an expectation that you're aware of the geometric formulas. So I'll cover, after we do this problem, I'll kind of write them all down real quick so you can see them all, at least the ones I think you should probably be aware of, and then we'll continue on. But yeah, for this one, I would say yes, there's an expectation that you know that the volume is x times y, and the surface area is just the areas of each side added together. So I'm going to take this constraint and I'm going to plug it in for y over here. So my volume equation is going to become volume equals x squared times 108 minus x squared over 4x. I know someone just joined, so let me give you guys the, sorry, let me give you the attendance again. Here's the attendance again. So let's take that equation. Let's use the other side of the board. Oops. So the volume is given by x squared times 108 minus x squared over 4x. Double check. That feels like I'm making a mistake somewhere. Nope, we're good to go. Okay. So the reason we do this is so that we can have a function of one variable. Right now the volume just depends on x, and we know how to maximize or minimize a function of one variable. Right? That's where we take the derivative, set it equal to 0, find the critical values, and then we test to see if it's a max or a min. Your teacher may or may not stress that point. I've definitely had teachers in the past who really stress the point that you have to show it's a maximum if you want it's a maximum. Almost all the time, if they're asking you to maximize a thing, the critical value that you find will give you a maximum. If they're asking you to minimize, will give you a minimum. There's like one problem in one book where they ask you to maximize something and there actually isn't a maximum. But for the most part, if someone is asking you to maximize, the one critical value you find is going to maximize it. If they're asking you to minimize, the one critical value you find is going to minimize it. I'll show you kind of how I would show the work. So I'm going to simplify this, and the thing I would do first is I would cancel an x here and an x here. So I've got volume is x times 108 minus x squared over 4, or I would distribute the x. I can write that as 108 x minus x cubed all over 4. Or maybe even better, volume is 108 x over 4 minus x cubed over 4. I was going to do something. I was going to write 1/4. That was fine. I just smelled the pen a little too much. Okay. Getting some fumes here. All right. So now that we've simplified this, we can take the derivative. So v prime, the derivative here, the derivative of 108x over 4, well, in fact, 108 divided by 4 is just 27. So this is really just 27x. And the derivative of 27x is just 27. And the derivative of x cubed over 4 is 3x squared over 4. Right? We don't have to use the quotient rule here since the denominator is just a constant. This is really just 1/4 times x cubed. And the derivative of 1/4 times x cubed is 1/4 times 3x squared, which is 3x squared over 4. And we're going to set that equal to 0. We would also check to see where it's undefined, but it's not undefined because there's no division by it, so we're fine. So setting this equal to 0, I'm going to add this over here. So I'm going to get 27 equals 3x squared over 4, multiply by 4, divide by 3. 27 over 3 is 9. 4 times 9 is 36. So x is going to be, technically x, the solutions to this equation are x equals plus or minus 6. But we know that we know that negative 6 doesn't make sense as an answer, right? If we're talking about, I know I erased that picture, where my picture was this, right? It doesn't make sense for the length of one side to be a negative number. That just doesn't fly. So x equal to 6 is our only real critical value. Now, we found the critical value. We're not done for 2 reasons, in my opinion. One, the question asked us to find the dimensions. We only found one dimension, which is x. So someone's asking, how did I get x squared in the formula for the volume? So I started with this volume equation here, which is x squared times y, because that was x times y. And then we solved for y using the constraint, which is that the surface area had to be equal to 108 square inches. We solved for y, so we got 4xy equal to 108 minus x squared. And then we divided by 4x, so that y was equal to 108 minus x squared over 4x. And then we took this y and we plugged it in for y right there, so that the volume was x squared times 108 minus x squared over 4x. And then we simplified it a bit. So I canceled an x, and then I distributed the remaining x, so x times 108 is 108x, x times x squared is x cubed. Then I divided each thing by 4, simplified a little bit, and took the derivative. So we got x equal to 6. So we still have to do 2 things. We need to find y. Now, finding y should be easy because we have an equation for y. Right? We have this equation, y equal to 108 minus x squared over 4x. So knowing that y equals 108 minus x squared over 4x, I can just plug in x equal to 6 and get y equal to 108 minus 6 squared over 4 times 6. 108 minus 6 squared is 36. 108 minus 36 is 72. 4 times 6 is 24. 72 divided by 24 is 3. So x equals 6 inches, I should say, and y equals 3 inches. And depending on your teacher, this might be enough work. However, some people, after you've found the value for x, want you to show that x equal to 6 inches gives us a maximum. In this case, right, because we're trying to maximize the volume. So, does x equal to 6 inches actually maximize volume? Well, there's a couple different ways to show it. The kind of standard way is to say, well, if I look back at my original function, sorry, words are escaping me for a second here. There's a limited domain for the values that x can take on, right? X has to be bigger than or equal to 0. I don't think x would even be 0, right? Because if x was 0, you'd have no surface area. So x has to be, okay, so we have to do the other one. Great. So x has to be greater than 0, and x has to be smaller than some upper limit. Probably, so x could be as big as the square root of 108, because square root of 108 squared is 108, and then y would be 0. That'd be a really weird box, right? Where you had just a flat piece of cardboard and no height. But it doesn't really matter. So here's what we're saying. This is our interval. I don't even really need the arrows. I guess I can just do points. So they're open points because we don't actually get to those values. So here's 0. Here's the square root of 108, which is a little bit bigger than 10. And then in the middle, here's our critical point at 6. And so I can look back at my derivative, v prime, which I know I have erased because I'm really smart. our derivative, which was 27 minus 3x squared over 4. Is that correct? Yeah, it is. And then we could test. Say, okay, pick a number smaller than 6, like 1. 27 minus 3/4 is definitely positive. Right? This is our derivative sign term. Pick a number bigger than 6, like 10. I can't go 2 there. I can't go beyond this. If it's 10, 27 minus 3 times 10 squared is 300, or 75. 27 minus 75 is definitely negative. So on the interval, on the domain of the function, it should say, left of 6, the function is always increasing. Right of 6, the function is always decreasing. It means we have to have an absolute maximum there. Not just a relative maximum, but an absolute maximum. And the way we can say it's an absolute maximum is because on the whole domain of the function, it's always increasing left of 6 and decreasing right of 6. This only works if you have just one critical value, right? Usually you use this is like the first derivative test. I usually use the first derivative test to show if you have a relative maximum or a relative minimum. But if you have one and only one critical value, you can use the first derivative test to show that this is an absolute maximum. 6 would not be the inflection point. 6 would be where we have a maximum in this case. So x equals 6 gives us a max, and that's it. So to answer the question, the final question, the dimensions that maximize volume are x equals 6 inches and y equals 3 inches. Notice that we didn't actually find the maximum value because we weren't asked to. We totally could, right? We would just find the maximum value by doing 6 times 6 times 3, but we don't need to do that if they don't ask us to. Are there other questions about this example before we move on to another one? Okay, let's look at another fairly typical example. Let's start with this. So I'm going to ask this question slightly differently than the previous one. It's still the same idea. So the question here is going to be, sorry, where'd you go? What is the area of the largest rectangle that can be inscribed in a semicircle of radius 5? So once again, we're going to draw a picture. So typically if I'm, sorry, I forgot I was going to talk about the different shapes. Let me do that first, and then we'll come back. But one of the things I was going to say here is that usually when you're drawing like a semicircle or a circle or a triangle or anything, if anything two-dimensional, it usually makes sense to kind of center things at the origin of your XY axis. So let me talk about the shapes real quick that you probably are expected to know things about. So let's see. We have, in 2 dimensions, we have squares, we have rectangles, we have circles, and we have triangles of various sorts, which can be kind of funky. And so here's what I imagine you're expected to know. The area of a square is x squared. The perimeter of a square, or the perimeter is the word I use, is 4x. The rectangle area is xy. Perimeter is 2x plus 2y. For a circle, the area is pi r squared. The perimeter, which we call the circumference, is 2 pi r. And then for triangles, you really only need to know the area is 1/2 the base times the height. Typically, we don't ask about the perimeter of a triangle. And then in 3 dimensions, we have the following sort of shape. So we have a cube, where all the sides are the same. The volume is x times x times x, which is x cubed. The surface area is just the area of all the sides together. So it's x squared for each side, and there's 6 of them. So it's 6 times x squared. You can also have a rectangular box where all the sides have different lengths. Although usually for a rectangular box, in this class, typically we're saying one of the sides is square, otherwise there's too many variables usually. So it's typical that you have a square base and a non-square other side. I'm calling this the base because that's how I drew it. So here the volume is x times y, and the surface area, if it has a top, right, if I have all 6 sides, is going to be, there's an x squared here and an x squared over here, so it's 2x squared, and then there's an xy and xy and xy and xy, so it's 4xy. A couple more shapes. I'm gonna have to erase on the left-hand side here. So we have a sphere, again, where the radius is r. The volume here is 4/3 pi r cubed, and the surface area of a sphere is exactly 4 pi r squared, which is kind of interesting. It's basically the surface area of a sphere is exactly 4 big circles worth of area. Also, something I've noticed over the years, which I think is kind of neat, is that specifically for the circle and the sphere, if you take the derivative of like the higher dimensional thing, you get the next lower dimensional thing, right? So the derivative of area is circumference for a circle. The derivative of volume is surface area for a sphere. It's kind of neat. I don't know why it is that way, but it is. It doesn't work for other shapes at all, just for that, those particular shapes. All right, 2 more shapes. One of them, so usually triangle things are kind of like, we don't like you. So for a cone, where the height is h and the radius is r, the volume is 1/3 pi r squared h. And we don't typically talk about the surface area. Someone could, but they would have to give you the formula for it. And then the last shape is a cylinder. Well, again, with a height of h and a radius of r. The volume here is just pi r squared times h, right? It's the base area of the circle times the height. The way I kind of remember the cone is that it's just 1/3 the volume of a cylinder with the same dimensions. And then the surface area here is kind of funky. So surface area here, assuming it's closed, like sometimes people say an open top cylinder because they're thinking like of making like a can to drink out of or a cup to drink out of. But if it's closed top cylinder, you have an area of circle on top, area of circle on the bottom. So you have 2 areas of circles, which is 2 times pi r squared. But then you have this around part here. And the around part can be kind of weird to think about. I think about it as being like a roll of paper towels. And if I take one paper towel off the roll and unroll it, what shape do I have? Well, I'm going to actually move this here. If I unroll a paper towel, where I cut it there, I have just a rectangular shape. Sorry, I want to make this longer. Erase all this. I'll just do it over here. Sorry, I have a rectangular shape. Where the height of the rectangle is still the same as the height of the cylinder, but the length of the rectangle is how far around paper towel run around the roll, which is exactly the circumference of the circle. So the area of this part here is 2 pi r times h. And so the surface area of the cylinder is 2 pi r squared plus, let me just write it down here. It's 2 pi r squared plus 2 pi r h. And these are the geometric formulas I think you're probably responsible for knowing about. So that took a little longer than I meant for it to. Let's see if we can get through this other optimization problem. So, what's the area of the largest rectangle that can be described in a semicircle of radius 5? I'm going to draw my semicircle. It's got radius 5, so it's hitting at the point 5, 0, 0, 5, negative 5, 0. And we've got some rectangle, which is sitting here like this. And you could draw it smaller, right? So it's not, I should have paid more attention to geometry. You could make the rectangle so it's not touching the corners, but then you're not going to have a rectangle with the possibly biggest area. So we definitely want to draw it so it's touching the corners. We know that this length here is 6. And I'm going to call this point that's touching the circle x comma y, so that I have a way of writing the area of the rectangle. So the area of the rectangle is the base times the height. The height is y. The base isn't x. The base is 2 lengths of x. So the area of the thing I want to maximize is actually 2 times x times y. And now, just like before, we have, well, I didn't actually say this last time, but what I should have said last time is that we had like for the volume, right? The volume had an x and a y, right? It was x squared times y. And we're trying to maximize the function. It needs to be a function of just one variable. In the same sort of way here, I have area as a function of 2 variables, and that's problematic. I need a constraint so I can write it as a function of 1 variable. So how do I get a constraint? Well, here we're constrained by the fact that we have to be in this circle. So specifically, the way I'm thinking of it is this point xy has to be, oh, sorry, I wrote 6 here instead of 5. Crazy, sorry. Right, this point has to be on the circle, meaning so you can either use the equation of the semicircle, or you could say Pythagorean theorem, x squared plus y squared equals 5 squared. Which is literally how you write the equation of a circle centered at the origin with radius 5. So you could use Pythagorean theorem, or you could be like, I know what a circle is. And then I'm going to solve for one of those. It doesn't matter which one we solve for here. Typically, if we have a choice, we usually like to isolate y because it's just we're more used to working with x. So y squared equals 25 minus x squared. And then I can't just take the square root of each part. I have to say y equals the square root of 25 minus x squared. And specifically, so usually be plus or minus, but since we know it's the top half of the semicircle, it is the plus part. So I'm going to plug that, so I should say this here is my constraint. I'm going to plug this y into y up here. So things are going to get a little bit messy. My new area equation is going to be 2 times x times the square root of 25 minus x squared. It's also worth noting that since I'm thinking of x as being this point here in the first quadrant, the x has to be between 0 and 5. It can't be any bigger than 5. It can't be any smaller than 0 because we can't go negative. Okay, I want to take the derivative of this and set it equal to 0. I know we're out of time, so I totally understand if you have to go, but I would like to finish this problem for you if you can stay. So feel free to leave if you gotta leave, but please stay if you can so we can finish the problem. It won't take more than a couple minutes. Although the algebra is a tiny bit messy. So here's our function. Area is equal to 2 times x times the square root of x squared. 25 minus x squared. Kind of fun to go all the way around like that, not gonna lie. Which I should really write as 2x times 25 minus x squared to the 1/2. And I'm gonna have to use the product rule and the chain rule here. So product rule, derivative of 2x is 2 times this left alone, plus leave the 2x alone, multiply by the derivative of this, which is going to be, I got some stuff to the 1/2. The derivative is 1/2 times my stuff to the negative 1/2 times the derivative of that stuff, which is negative 2x. Okay, we need to simplify this. And the way we actually need to simplify this is we need to factor out as much as we can. I can factor out a 2. Let me use a different color to do that. I can factor out a 2. And I can also factor out a 25 minus x squared to the negative 1/2. That's always the smaller power. So look what I get. I get 2 times 25 minus x squared to the negative 1/2. From this first piece, I don't have a 2 because I factored it out, but I do have a 25 minus x squared to the positive 1. Right? Because if I divide out a negative 1/2 power, 1/2 minus negative 1/2 is positive 1. But really the way I actually think about it is you multiply this back in, you would add these powers, and negative 1/2 plus 1 gives you positive 1/2 like we had. Here, I'm going to factor this 2 out. I'm also seeing I have a minus sign here. I'm going to say it's minus. So factor that 2 out. This 2 cancels with that 2. So I get a minus x, and that's it, because this part here factored out. So rewriting this, here's what I've got. I'm going to bring this out to the denominator. So I've got 2 times, oh, sorry, I missed an x. It's x times x, which is x squared. Sorry about that. So on top, I've got 25 minus x squared minus x squared minus 2x squared over this 25 minus x squared to the positive 1. Okay, setting this equal to 0. We get, well, I have to set the top equal to 0. So you get 25 minus 2x squared equal to 0. You get 25 equal to 2x squared. I get x squared equal to 25 over 2. So x equals the square root of 25 over 2, which is 5 over root 2. Or 5 root 2 over 2. Oh, thanks. You guys are on it. Appreciate it. So we should probably check to see if it's a maximum. So the way we check to see if it's a maximum, right? If we're on the interval from 0 to 5, we've got 5 root 2 over 2 in the middle. And if I plug in a number smaller than 5 root 2, I don't know exactly what 5 root 2 over 2 is, but I know 1 is smaller than it. So I plug in 1, I see that my derivative here, a prime, 25 minus 2 is positive, 25 minus 1 is positive, so it's definitely positive over here. Big number larger than 5 root 2 over 2, which I think 4 is bigger than 5 root 2 over 2. I don't know, 5, well, so root 2 is like 1.4. 5 to 1.4 is 7. 7 over 2 is like 3.5. So yeah, 4 should be bigger than that. So plugging 4, 25 minus 2 times 4 squared. 2 times 4 squared is 32. 25 minus 32 is negative. And the bottom is still positive because 25 minus 4 squared is positive. It's negative, which means it's increasing, decreasing, which means we have a maximum at 5 root 2 over 2. Again, I'm not sure if the professor really cares about you doing this, but if he does, this is how you do it. So then to go back, so we found the x value, and now we have to go back and actually answer the question. So the question said, what's the area? Right? It didn't say find the dimensions. If we want to find the dimensions, we can totally find y by just plugging in x here and getting y. If we want to find the area, we can just plug in x here and find the area. So let's do that. So the area is going to be 2 times, x was, I forgot, 5 root 2 over 2. So we're going to get 5 root 2 over 2 times the square root of 25 minus 5 root 2 over 2 squared. And this actually simplifies really nicely. These 2's cancel. You get 5 times root 2 times 5 root 2 over 2 squared is 25 times 2 over 4, which is 25 over 2. 25 minus 25 over 2 is 25 over 2. So you end up with 5 root 2 times the square root of 25 over 2. But that's just 5 root 2 times 5 over root 2. Those cancel. You get 25. So kind of a lot of work, but not too terrible. Yeah. All right, that's all I've got for today. Monday, we can talk more about optimization. Also, if you guys have questions you want me to talk about, like I can make a video, just ask. I can make more optimization videos if there's specific things you want to see, or L'Hopital's rule, or there was something else. I can't remember what it was. But if you have things you want to see, let me know and I will try to make that happen for you. All right. Fill out the attendance and I will talk to you guys on Monday.